So today I will be explaining this CopyNet idea in supervised learning. This network is called CopyNet, and there are similar ideas like that, such as CopyNet, but today I will be explaining this article, incorporating copying mechanism in sequence-to-sequence learning. Because sometimes we have some words that are out of vocabulary, and we just want to copy them because we can use this technique. But you may guess that this copy mechanism, because it's a kind of combination of two actions, copying and generation, would result in a discontinuous and non-differentiable loss function, so you cannot train it. But you will see that you can use some tricks, like just adding in mathematics, can be used, and we don't have any problem. So the CopyNet can nicely integrate the regular way of word generation in the decoder with the new copying mechanism, which can choose subsequences in the input sequence and put them at proper places in the output sequence. For example, hello Jack, my name is Chandra Lekha. Nice to meet you, Chandra. So it's just copying this. It may not have this word or my name Farshad in their vocabulary, but it can just copy that. It doesn't perform exactly as we expected. What do you mean by doesn't perform exactly? So it can just copy from a particular span, from here to here, of the input utterance. So you should be familiar with some concepts in PyTorch in order to implement it. And this batch matrix product, batch matrix multiplication, this is multiplication. This batch matrix multiplication product is this batch matrix product, let's say. The idea is that you have two matrices and you just multiply it. But we are also considering the batches, the elements in the batch. And there is another thing, NLoss. It means that negative log likelihood loss. So it's useful to use NLoss in this project as the loss of your model. And the training is very standard. We have for any epoch, and of course we use teacher forcing. I sometimes use teacher forcing of 0.5 because I want to facilitate, I want to enhance and increase the speed of training. Of course, some people argue that teacher forcing would not be mathematically justified, but we do something in machine learning such as stochastic gradient descent and so on, but it works. So here we loop over the epochs, and then for batches, for elements in the batch, we say that, for example, we modeled by Encoder Decoder. This is the class that we have defined, and what we get from that is we have also a loss function. We have used that NLoss loss function, and finally backward and step. So everything is standard. But so what is this CopyNet idea? The CopyNet idea is a combination of your classic generation and also the copy mechanism. So the output is from generator and also from the copy, the output of your decoder. So for the generator, we use the just standard attention mechanism. And so you have seen this. This is context linear combination of your hidden states. And this is called energy, or sometimes called alignment, sometimes called score, everything people say. And from a modeling perspective, the copying operations are more rigid and symbolic, making it more difficult than soft attention mechanism to integrate into a fully differentiable neural model. This is the problem that I was talking. So we present CopyNet in a differentiable way. How? We just use addition with copying mechanism which can be trained in an end-to-end fashion with just gradient descent. So the encoder of the copy encoder is very standard as usual, and you see everything is usual. We do embedding because if we don't have a word-to-vec, we always use this embedding layer in order to learn it end-to-end. Then we go and use GRU because GRU is faster than BiLSTM and LSTM and those things because it has less parameters, and that's why we are interested in GRU so much. So before giving it to GRU, as I told you in previous lectures, we do packing the padded sequence because some sentences are not equal, so we make them into some packs. So this one. So this is how we create our batches, because we make sure that the sentences inside a particular batch are have the same length. And if they are not, we add the pad. So padding and then packing. But after we have created the output and hidden, we should pad the pack sequence. So we come back to the pad what we have done. So it's like Fourier and Fourier transform and inverse Fourier transform. You do something and then you come back. In the decoder section of the CopyNet is a bit interesting. So the prediction predicts the words on a mixed probabilistic model of two modes. Let me explain it here. Let me explain it later because we don't see it. So the encoder decoder. So we have encoder. This is a standard, and we use this attention decoder. This is a standard, but we also have the copy mechanism, which is CopyNet decoder. So we have two decoders, so we add them together. The forward method of this class is just we use encoder and decoder. So this is the architecture of that. As I said, we just add the probability of your decoder output to the probability of decoder output, but for the copy. C stands for copy. G stands for generator. The usual standard generator that we all know. So if we just add these two probabilities, we can combine these two ideas. The idea of just copying what is inside the utterance, the spans of the input utterance, and also the generator that we always do, we're always familiar with. And so the probability is just the sum of them. And so you see there are some words in your utterance. For example, this word is not in your vocabulary. V is your vocabulary. This word is not in your vocabulary. So X is for your utterance, input utterance, and V is for vocabulary. And sometimes there are some words they're in an intersection. It means they are both in your vocabulary, some very useful words, but they are also, you can also copy them. So it's in their intersection. And we model these via a given S of t, which is the decoder, hidden state, and output, and the context. C is here is context. It's not copy. Here's context. C is here is context. So, but C is here is copy. So you see, the notation is not good. So when you add these probabilities, this is a standard, but here is a little bit tricky. We will explain it. And also we have normalizing factor z here. And so in the generate mode, we just used a simple function in order to relate what is in the output with the we just use Bardano attention mechanism in 2014 that has got more than, I think, 300,000 maybe citations. So it's very important. But the CopyNet mechanism is like this. The reason we use HJ is just a trick. It's just hidden states in order to represent the input utterance. And S of T is the hidden state of the decoder. And in the state update, we just use a trick. In order to just simply to give the embedding for the input of the decoder, we augmented with key variable. And it is just a linear combination of your hidden states. It's a kind of creating some kind of context. And the weights are like this. And so the decoder part, we have embedding, and then we have attention mechanism. This is for generation, and then for copy mechanism, and then we combine them, and we says, okay, now we have the probability of, after doing softmax, we can understand what is the probability that a particular word is what. So the decoder part, we have here, everything is standard, and here we are using teacher forcing, and what is this mask scatter? What is these? These are the things that you should be familiar with because we use it a lot. And here is a CFD, the context. It's a linear combination of hidden states. So batch matrix multiplication is your context. So it's just multiplication of attention weights. What are your attention weights? Your attention weights are alpha. And your encoder outputs. What are your encoder outputs? These are encoder outputs. So if you multiply them, you get the context. And what are your attention weights alpha? You can also use this attention weights is the softmax because e to the something, if you sum them. So this is the softmax of something. And then here the attention score. Attention score is just here. The multiplication, or sometimes people call energy, the multiplication of your encoder outputs and the transform hidden. And what is the transform hidden is the attention W. So it's basically we are just multiplying H of T with the ST to get the score. And here we can also use the dropout and those things. So in the decoder part, we have the copy mechanism. We have attention and copy. So we just want to combine them. And the generate mechanism is like this. So we are implementing this. So when we say, so this is the score, and we generate these probabilities. And finally, we add them. As I said, we just add these two things. It makes it smooth. So we are adding the copy problem, the copy probabilities. This is the copy probability. And also the generation probability. This is the generative model that we always do in our attention since 2014, that Bardano created that beautiful paper that has got more than 300,000 citations. And finally, we get the top K1. It's a greedy and what else is important? So everything from here, we are just using selective read that I explained. We are implementing this in this part.